last time we did this conceptual understanding of the modes where we said that only discrete angles are allowed, even though any angle greater than the critical angle. So, suppose this is the critical angle at the interface, ideally any angle that is greater than critical angle should have been guided, but that does not happen because of we did some very preliminary ray optics understanding to say that there are only certain specific angles that are allowed in the system, and those specific angles are called as correspond to the modes of the fiber, transverse modes of the fiber. Okay. But now these transverse modes, we still do not know what is the spatial pattern, and I said that what distinguishes the transverse mode is the spatial xy pattern of that mode. Right. We have still not, this analysis will not give you that, it is just telling you that there are only discrete modes possible. It can also potentially tell you at what angles are each of these modes supported, but it is not telling you how the transverse profile of the modes are looking like. So, the next is to next couple of lectures, I hope we will not need couple of lectures, but is to derive the transverse modes of a optical fiber. Okay. So, what is the objective? We want to now find out the spatial distribution of the energy that is carried by the optical fiber, given a certain core diameter, given a certain refractive index profile, right. And the next part, so the transverse profile needs to be worked out is what we are saying. This part, the derivation is directly taken, I have used the same notations as that of fiber optics book by Professors Gattak and Tyagarajan, right. I think it is called Introduction to Fiber Optics by Gattak and Tyagarajan. It is the same, exactly the same treatment. Okay. So, how do you get the modes? The transverse distribution is given by solving the Maxwell's equations, right. It is the wave equation solution subject to the boundary conditions. What are the boundary conditions we have? You have the fiber, you have a circular cross section, you have the fiber. So, you are not looking at what happens at this interface, we are not talking about that boundary, we are assuming that it is infinitely long on either sides, and you have a core of refractive index N1 and a cladding of refractive index N2. So, there is a core cladding boundary, that is N1, N2 is different at the boundary. So, that boundary condition is what we need to consider. Now, as we said earlier, each mode is characterized by different spatial distribution. So, the objective is to find out what the spatial distribution is, and once you have assumed or you calculated the transverse spatial distribution. So, the transverse spatial distribution of a fundamental mode is going to look like this. So, on the y axis here it is the intensity or the electric field, on the x axis here is the radius, along the radius. This is how you will get as a result of the fundamental mode. The assumption we are making is that the fiber is kept straight, okay, for infinitely long distance, so that the transverse profile, whether I solve it at this location at z is equal to some 1 meter location and at z is equal to 1 kilometer location is the same. So, that is the assumption we are making. It does not change during propagation. Of course, whenever there is a bending, what happens? In a real fiber there could be bends. What happens when there is a bending? The mode actually changes, and we will see later how to account for the changes in the mode when we are doing the when the fiber bends. Okay. So, one classification based on whether one mode is supported or multiple modes are supported is a single mode fiber and a multi mode fiber. A single mode fiber is a fiber that supports a specific mode for a given wavelength. Okay. Wavelength is important, we will realize why wavelength becomes important. So, a fiber is single moded at a given wavelength provided it supports only one transverse profile at that wavelength, and the same fiber is multimoded, the same fiber could be multimoded at another wavelength, or in general multimode fiber is a fiber that supports more than one mode for a given wavelength. Okay. And typically what is different, if the wavelength is the same, a single mode fiber, the dimensions is 8 to 12 micron core and the cladding dimension is 125 micron. and the core for a multimode fiber is 50 to 200 micron depending on the number of modes it is supporting, and the cladding dimension is typically, if it is a 50 micron core, it is typically a 125 micron cladding, but you do have 200 micron or even 400 micron core, but then the cladding becomes proportionately larger. Of course, the plastic fiber that you have seen, that is much larger dimension than these, okay, that is also a heavily multimoded fiber. One thing to also observe is that, as I said, I will reiterate the fact that it's whether it is single moded or multimoded is dependent on the wavelength. Now, another thing to notice is that, you know, when we solve the wave equation, we are solving at these boundaries, okay, we are not solving for this boundaries. The cladding dimension is kept so large that the wave, the guided mode has attenuated completely by the time it reaches the cladding air interface, or usually in fiber it is not air, there is a plastic coating, a polymer coating, that is what is making the fiber flexible, because otherwise fiber is glass, if you bend it should break. It does not break because the fiber has a polymer coating, and the polymer coating is making it flexible. So, usually you have a refractive index N1, you have a refractive index N2, and there is a refractive index N3 outside that. So, when you apply boundary condition, you are not really worried about this boundary condition, simply because the cladding dimension is very large. Now, if you are trying to propagate energy in cladding for some reason, then I have to worry about this boundary condition. But usually for normal communication applications, you will worry only about the core cladding boundary and not the cladding outer cladding boundary or air boundary. For instance, if you are using fiber lasers, you are using fibers for making lasers, there is a class of fiber lasers where you are pumping the lasers by putting energy in the cladding, not in the core, right. So, there you have to worry about this interface and what are the modes of cladding modes and so on, right. But in general, for communication applications, you do not really worry about cladding air interface, all your boundaries are core cladding interface. So, we take so this picture shows the refractive index profile. So, refractive index is high in the core region and it is low in the cladding region, and in the outside region it is actually further lower, and this could be air or it could be a polymer, and correspondingly for a single mode fiber the core size has reduced, and so this profile has changed. Now, this profile is what is called as a step index fiber. If the fiber has this kind of refractive index profile, it is called as a step index fiber, because the refractive index is of the step shape, whereas you could also have other profiles, and the reason why you want other profiles we will talk about later. Now, so for we are going to solve the modes or find out the modes of a step index fiber. Now, a step index fiber, the refractive index as a function of radial coordinate is N1 for 0 to A. So, A represents the core core diameter or radius. When I say 0 to 0 less than r less than A, what should A represent? Radius of the core. So, A, remember, you will keep needing this A whenever we say A, it is radius of the core. There are a lot of equations that we are going to be writing. So, you can probably pay attention to how these equations evolve. So, the other approximations that we are using is also that it is a scalar wave, means we are not solving for different polarizations. This is single polarizations, which means that my answer is not dependent on which polarization I launched. The wave can be of any arbitrary polarization. So, in that sense, you also you say that it is, these are LP modes, linearly polarized modes. Even though it says linearly polarized modes, the word can be a misnomer. It does not mean that it works only for linear polarization. It simply means that the answer is the same irrespective of my polarization state of the input. The modes are assumed to be nearly transverse, meaning if you have remember your modes of a rectangular waveguide, you would have components along the longitudinal direction also, right. So, you do not have any component of electric field along the longitudinal direction, all the components of the electric field are along the x and y direction, provided your z is the direction of propagation. and that is happening because of this weakly guiding approximation. Now, what is this weakly guiding approximation? Do not go by the English and think that the mode is, I mean the fiber is weakly guiding and so all the energy is lost. It is not like that. It simply means that N2 minus N1 or N1 minus N2, N1 is larger than N2, N1 minus N2 difference is very small. Very small, it is typically of the order of 10 power minus 3. It is not that N1 is 1.5 refractive index and N2 is 1 refractive index. Remember, you are doping the fiber to change the refractive index. Even in that context, I told you that the dopant concentrations are such that the change in index that you are having is typically 10 power minus 3, which is like 0.1% is the change in refractive index. That is the order of magnitude for single mode fibers. Okay. And or the analysis we are doing are for weakly guiding approximation. So, which means you have to remember that if you happen to have a fiber where N1 is very different from N2, whatever we are going to do now is not going to hold good. For instance, if I take a plastic fiber where there is a very large difference, this analysis may not hold good. Okay. And scalar wave, which means that we are not solving the vector wave equation, we are using a scalar wave equation, which means that the electric field what we are solving for has a x component and a y component, and it has no z component, and what we are saying is that the Ex component and the Ey component of the electric field are the same. Okay. So, that is the meaning of this whole thing. Ex and Ey are identical. There is no the profile that you get, the transverse profile you get, you cannot say whether it is for Ex or Ey, it is the same for Ex and Ey. That is what we are assuming. It is a spherically symmetric system, so it is okay to have that assumption. All right. So, now we get into the rigorous math. Okay. So, first of all I need to write the wave equation of the electric field. This one is, I am writing it as psi following the notation used in the book, but this actually represents the electric field E, and I do not have to say whether it is Ex or Ey, because we just said that whether it is Ex or Ey it is going to be the same. So, I do not have to distinguish between Ex and Ey. So, this is a regular wave equation, right. It has, the wave has x, y, z component, is propagating along the z direction, it has a time dependence and it has a profile along the x, y, which is what we are trying to find out. Okay. What is the z dependence of the wave? There is a propagation constant for a wave, so there must be a beta z for the wave. I already said that it is nearly transverse, so there is no z dependence for the wave, it is only beta z that comes in the z dependence, and this is your regular wave equation. Plane wave is not a solution because typically we say in your first class of electromagnetics, you say if I have a wave equation, plane wave is one solution for this, but I can't say plane wave is a solution for this simply because it is a non-homogeneous medium, right. What is a non-homogeneous medium? A medium where the wave is seeing different refractive indices. If it is seeing the same refractive index, you call it as a homogeneous medium. In a homogeneous medium, plane wave is a solution. In a non-homogeneous medium, plane wave is not a solution. Okay. This is why plane wave is not a solution, because your c square is mu naught epsilon naught n square, where n is a function of x, y now. In a homogeneous medium, n is a constant. So, plane wave is a solution. Okay. This n square, now it is depending only on the transverse coordinates, because you have the fiber and the you are assuming that there is, you just, I already told you the assumption that the fiber is considered to be uniform along the length. So, it does not matter whether I solve at a specific z location, right. So, because n is a function of only x and y. It is cylindrical symmetry, so we will have to rewrite this equation not in x and y, but in r and phi, because the system is a cylindrically symmetric system, which means this wave equation has to be written in cylindrical coordinate system. So, instead of x, y, z, you should have to you should write in a cylindrical coordinate system, it is r, phi and z. R is the radial coordinate, phi is your azimuthal coordinate in the cylinder, and z is your this this is radial coordinate. If I draw the cross section, this is the radial coordinate, this is the azimuthal coordinate, and the propagation is along the z direction, third transverse direction. Okay. So, there is an expression for del square in the cylindrical coordinate system, and you can use that expression. There is no longitudinal component of electric field. Psi has only transverse component r phi. So, psi is dependent on only on r phi. So, I can separate out the dependence of r phi and t and z. So, I separate out psi r phi, and of course, t dependent is coming from j omega t and z dependence is beta z. What is your objective? Objective is to find out the possible values of psi. So, what is the unknown here? Your objective at the end of the day should be to get psi r phi and beta. It is a linear system, so you do not think that new frequencies are created. So, omega is constant, it is depending on what is the launched frequency, but beta is something that you do not know for the system inside. Even though the core index is n1, the beta of the mode is something different. So, the unknowns are this as well as beta. So, throughout this derivations, we are actually looking to solve for psi and beta allowed modes. So, what we are going to do is we are going to substitute this solution into the wave equation, right, and you have to solve this second order differential equation. And as I said earlier, now what we will do is you will replace this del square in the cylindrical coordinate system, and del square in the cylindrical coordinate system takes this form: 1 by r del r del psi by del r plus 1 by r square del square by del phi square plus del square by del z square, right, and del square by del t square remains as it is. So, I will have to substitute this psi, which is this, into this equation. So, for instance, if I substitute this, so this everywhere wherever I see psi, I will say I will substitute this as del by del r of psi, which is a function of r phi e power j omega t minus beta z. I will keep substituting like that. And because it is a derivation with respect to r, this e power j omega t minus beta z comes out, right. It comes out in this term, it comes out in this term, it comes out in this term. There is an e power j omega t here. But here when I am doing second derivative here, I have to do j omega twice. That will be the because it is a del square by del t square, right. So, I substitute here. So, I have just rewritten the wave equation right now. So, 1 by r del psi by del r, this is exactly what I said, right, del psi by del r e power j omega t minus beta z. In the second term, you see that it is a del square psi by del phi square. So, I have this. The third term is del square psi by del z square, right. Now, del z is I can this one is not dependent on z. So, that comes out as a constant, and then the derivative of beta z is minus j beta the whole square, twice derivative. And similarly, on the right side I have twice time derivative. So, that twice time derivative will come out to be j omega the whole square. The rest of the wave equation is as it is. Okay. Now, what you can take out as common is e power j omega t minus beta z, right. So, you can just write out the coefficients of e power j omega t minus beta z everywhere. What do you get? I will not have this, I will not have this, I will not have this, I will not have this. What will I have? 1 by r del by del r del psi by del r. Now, I can take the derivative of this. Now, what is the derivative of this? This would be r del square psi by del r square plus del psi by del r, and then there is a 1 by r. So, because of this 1 by r, I will have this 1 by r. Here I do not do anything. Here I write it as minus beta square psi. Here I write it as minus omega square. Okay. So, when I do this, this is what I get. Along the radius, so the question is, does n depend on phi? So, in the fiber, if you take the cross section of the fiber, the entire cross section has a refractive index n. It is not, there is no angular dependence here. So, n does not depend on phi. Okay. So, the simplified form del square psi by del r square plus 1 by r del psi by del r plus 1 by r square, which is this term written as it is here, and here I have a minus beta square and here I have a minus omega square, of course along with mu naught epsilon naught n square r. Okay. So, if I call this mu naught epsilon naught omega square, this is nothing but the free space wave number square, right. So, if I call this whole thing as k square and bring it to this side, I get k square minus beta square, right. So, that is what I have written, k square minus beta square. Of course, there was an n square r here. So, k naught square n square minus beta square psi. So, that is this term. Right side is 0 because I brought it to the left side. Now, this is the equation that needs to be solved. What is unknown? Again, we will keep reminding ourselves what is unknown, what is known. Psi is unknown, beta is unknown. It is a second order differential equation in how many variables? 2 variables. Which are the variables that you do not with respect to your, you have your r and of course you have your phi. Now, if you have a second order homogeneous differential equation, one way of solving it is, assuming this will work only if it is a homogeneous equation, is to do what is called as a variable separable solution, which means you say that okay, we already reminded ourselves of the objective. So, this says that I can now write my psi as it's a function of r and phi, but I can say that it can be written as a product of 2 functions. First function which is a function of r alone, second function which is a function of phi alone. This is a standard technique for second order differential homogeneous differential equation. Okay. If I do that, how would this equation get modified? What will I have? Del square psi by del r square will become del square r by del r square, but while doing this differentiation I should take phi as a constant. Will I get phi square? No, it is just a scalar multiple. Similarly, when I do this, I will again have phi outside and this will be del r by del r. Then I will have del phi by del phi. So, r will be outside, right. So, that is what you do, phi del square r by del r square, 1 by r phi. Okay, there is a capital phi and there is a small phi. Okay. So, this is all capital phi, take care of that, whereas a variable is a small phi. Okay. And the third term is r times del square phi by del r square, plus this term remains as it is, but every time I see a psi I replace it with r phi. Okay. Now, I can simplify this by dividing it throughout by what? R phi, capital R capital phi, and also I can multiply it with r square, so that this term will now look like something which is a function of only phi. So, I multiply it by r square divided by r phi. When I do that, I do that operation of multiplication and division, I get r square by r by r, this sorry, I multiply and divide, I will get 1 by phi del square phi by del square phi by del phi square plus this, because I multiplied by r square I will have this r square here. Okay. Now, this is very interesting because this is the objective of variable separable method, that you are able to separate out the differential equation into 2 equations in 2 variables separately. What we are trying to do is that you see here these 3 terms are dependent only on r, whereas the term here is dependent only on phi. So, it means that a function of r plus a function of phi is equal to 0. That is what we are trying to say, and that can happen only if both of them are independently equal to something, some constant. This is a function of r, this is a function of phi, and you are saying that a function of r plus a function of phi is equal to 0, that can happen only if both of them are independently some constant. So that is what we are going to say. Since the variables are separated, you pull this to the other side, these two will become equal only if both of them are individually equal to a certain constant. Otherwise, you cannot have two functions equal to each other. So for all values of r and for all values of phi, right. So you could equate both of them to a constant L square. So if I equate this to L square, what I get is minus 1 by phi del square phi by del phi square is equal to L square, which is just the azimuthal part, and the radial part is this part equal to L square. So from the wave equation which had two variables, what you achieved is you separated out the azimuthal part and the radial part. You solve for the azimuthal part, you solve for the radial part, you will get the individual parts, multiply them, that will be your complete psi. Okay. Now what is the solution of this part? 1 by psi del square psi by del phi square is equal to a constant L square. Cos phi, cos L phi, is cos L phi a solution? Sin L phi a solution? I mean, this is a harmonic simple first second order differential equation which has a harmonic solution. Harmonic solution will have a cos L phi and a sin L phi as a solution, right. So the solution of this part should be of the form cos L phi or sin L phi, where L is an integer. See, that second derivative gave L square. When you do second derivative, it will give you L square, which is why initially you equated to the constant L square. Otherwise, there was no motivation of equating it to something like L square. Okay. So that is your radial part. There could be a constant, of course, there could be a cos L phi and a b sin L phi, but all these constants we will put together because your psi itself is r and phi. So you could have a constant here, which I am not writing right now. Now let us pay attention to what is this cos L phi sin L phi. So for L equal to 0, what happens? L square is a because L square is a constant, L must be a, of course if I do not have L as an integer, I will not satisfy this equation. Okay. So I will actually have L is equal to 0 plus minus 1 plus minus 2 etc. Right. But plus minus 1 and plus minus 2 may give you the same solution, in the sense that it will be minus sin L phi, or it will change only in sign, it will change only in phase, the form of the solution remains the same. But for L equal to 0, what is the solution I have? What does it mean? I do not have any radial azimuthal dependence. I will not have any azimuthal variation. Okay. I will have a so here it is not that phi equal to 0, you can't say phi equal to 0. If phi equal to 0, what happens? The wave equation itself, the wave itself reduces to 0. It simply means that the when L equal to 0, your psi is only a function of r, it is not a function of phi. That is what this means. And I could have, for this condition, I could have two orthogonal polarizations existing in the system. Because I said that my answer is independent of polarization, the solution is true for x polarization and y polarization. And you know that any arbitrary polarization state, you could be resolved into x and y polarization. So if we ask ourselves the question, for L equal to 0, how many degenerate modes are there? Now what are degenerate modes? Modes which the same property, cos L phi or sin L phi will have the same property, right. So and same polarization, so same beta, so same propagation constant. So for L equal to 0, how many degenerate modes do you have? I do not have an azimuthal variation, okay, and I can have two polarizations. So I can have two-fold degeneracy. What is degeneracy? Allowed modes with the same propagation constant, right. See, calculation of phi did not, it was irrespective of beta, it was irrespective of what my beta was, which means that whatever I get as cos L phi or sin L phi, there are two possibilities, right. cos alpha value and a sin alpha value. So, that is a two-fold degenerate, right. They have the same propagation constants beta, and each one of them could be of two polarizations, x and y polarization. So, what we are saying is, when you have L equal to 0, you can't distinguish between cos alpha and sin alpha. So, there is only one possibility that exists, and for the azimuthal variation, which is no azimuthal variation, and for that you have two polarizations. So, this mode is two-fold degenerate. Okay. Modes with L equal to 0 is two-fold degenerate. The factor of 2 is coming because two polarizations can be supported. So, question is, for L equal to 0, what is the solution? I still have to work out the radial part to find out the solution, but does not matter what my radial part is giving. What it means is that for L equal to 0, angular dependence degeneracy in that is fixed for me. We are trying angular dependence of what? We are talking about field. So, angular dependence of field is 0, which means that if I plot my electric field value of the radially, I do not know how it is going to look like, but along phi there is no change. That is what this means for L equal to 0. What happens? Okay, let us see if we understand this. What happens? What is the degeneracy of L equal to 1 mode? So, for L equal to 1, what does it mean? I will have either cos phi or sin phi. So, what does this mean? So, what are we talking about? We are talking about the angular dependence of the solution irrespective of what my radial coordinate is. We have still not solved the radial part. So, I will take a radius. For that radial part will tell me some strength. I do not know that yet, but I know that the angular part. So, for phi equal to 0, if I take cos phi, my field is going to look like the field is having a maximum value. For phi is equal to 90 degree, here at this point the field has to get reduced to 0. So, somewhere from maximum it has to get reduced to 0, right. At phi is equal to 180 degree, it should get negative maximum, and phi is equal to 360 degree, it should, so 180 degree, so this is 90, 180, 270, it is again 0. So, I should get something like this. This is just a polar plot of cos L phi, but I could also have sin phi. How would the plot of sin phi look like? Of course, this is not complete in that sense, because this is only angular dependence I am plotting. Actual field will have radial dependence also. What would sin phi look like? Will just look rotated with respect. So, how many fold degenerate this is? How many possible solutions, phi solutions will you have? 2 because of cos phi sin L phi, and each of them could be of x and y polarization. So, it could be 4-fold degenerate. What about L equal to 2? Again I repeat, 4-fold degenerate means there are 4 possible solutions for my electric field, which will give you the same beta, which will give you the same propagation constant, because the propagation constant is defined by the radial part, and we are not solving the radial part. Irrespective of the radial part, we are getting the phi part. For L equal to 2, what should it be then? How many fold degenerate should it be? 6-fold? Really? It will still be 4, because this will give me a dependence, only the angular dependence is changing, but I will still have for instance here cos 2 phi sin 2 phi. These are the possible solutions in the azimuthal direction, and each of them will have x polarization and y polarization. So, I will have 4 possible values of azimuthal variations, which will give me the same value of beta. The answer is 4-fold for both. We will understand this once again when we write the complete solution. Okay.